So one really pivotal set of skills that we'll be using almost throughout the course is unitary rate analysis. And in order to understand how to do that and the importance of it for math, we first have to actually look at, well, what is a unitary rate and then what will that mean? So what you may not actually realize is that in everyday lives, as in science, unitary rates are used all over the place. For example, when you go to the grocery store, if you look, there's a box of apples there. One box of apples would cost $6, which means that you could buy a box of apples at $6 per box. Similarly, you could go to the gas station and buy $1.29 per liter. So for every 1 liter of gas, you have to pay $1.29. Now, a rate always compares a quantity to one thing of another. So in other words, in a unitary rate, the second quantity is always a 1. 50 kilometers an hour really means 50 kilometers per 1 hour. 23 liters of fuel consumption per minute really means 23 liters per 1 minute. Even if that 1 isn't explicitly stated, it's actually there. Now, that might not seem all that important, and maybe it's not really all that intuitive why unitary rates are important, but here's the clincher, is that unitary rates can be inverted. In other words, you can take them and flip them over depending on what information you start with, and probably more importantly, what it is that you want to find out. So when you go to the gas station, the cost of the gas at the station is, oh, this isn't true, $1.30 per liter. And that's because most people either start by knowing how much gas can go in their car, so they know or start with the liters and want to be able to get rid of that unit, or they want to know the amount that they're going to pay, so they want to have the amount, the dollar amount, on the top of the relationship. But if you happen to go to the gas station and instead of wanting to know how much you're going to pay to fill it, you say to yourself, well, I have $10 and I want to know how much that's going to get me, what volume of gas that'll get me, then it's probably more important for you to flip that relationship over. In which case, I would know that 1 liter I would get for every $1.30. Or it would be about 87 cents, or sorry, 0.87 liters per dollar. In this case, that's when you start by knowing the size of your tank and you want to know how much you're going to pay. So unitary rates can be used in many different chemistry calculations, just like they are in physics. And if you have a density question, for example, we can use unitary rates and produce unitary rates in a couple of different ways. Unitary rates, again, remember, are anything that you can make that has a number value compared to a quantity of one other. So density, in this case, we went over last day, density is the mass in or per a given volume. In this case, our mass is 45.6 grams, and we're going to divide that by 10.2 milliliters. Now, this is not a unitary rate because it hasn't been divided through yet. In fact, what the actual unitary rate is, and I'm just going to clear the screen so that you can see what's there, is that there's 4.47 grams per milliliter. Remember that even though it's not written here, there is an imaginary 1. Notice what happens to the units in the calculation. Grams and milliliters are not the same unit, so they can't cancel out, so they both remain. Now, when it comes to doing unit analysis, and this is where I started with at the beginning of the slideshow, was saying that unit analysis is really, really pivotal here. It really involves the elimination of quantity or units common to the numerator of one value and the denominator of a calculation until you happen to get to the correct units. We'll get to a topic at almost the very end of the year, which is called stoichiometry, and this is a process that we will do over and over and over again, just in repeated steps. And if you can learn to do this now, that unit will be a cinch. So let's try using unitary rates and unit analysis for this following question. So light travels at 300,000 kilometers per second. And how far will light travel in 1 femtosecond? So before we start, we need to go back and think about, well, we learned about metric conversions. And I know that 1 Fs must be connected to some other unit. Now, I don't have femtoseconds up here in my unitary rate. I have just plain old seconds. So I need to go from femtoseconds to seconds. 1 femtosecond is 1 times 10 to the negative 15. That's 1/millionth of a billionth of a second. So I have 1 times 10 to the negative 15 seconds, and I have a relationship that involves kilometers a second. It's asking me how far it will go, so that means that distance doesn't have time associated with it, so I need to be able to get rid of or cancel off this second unit. In order to do that, I need to do unitary rate analysis. I'm going to start by drawing an X and a line. Anytime you want to change your units, you draw an X and a line as a starting point. The unit that I have to get rid of here is a second. In order to cancel that unit off, I need to have it in the numerator at the top and in the denominator. So I'm going to use the unitary rate so that the second part is on the bottom. That means that I'm going to have to put the 300,000 kilometers on the top. Remember, when I look at that even though there's nothing written in front of the S, I know there's actually a 1. Here, seconds and seconds will cross out, and I'm left with units of kilometers. And putting that through in my calculator, and I'll be able to do this in my brain because this is 3 times 10 to the 5. This means that this is 3 times 10 to the 10 kilometers. Negative 10 kilometers. Now, 10 to the negative 10 kilometers isn't really an easily measurable unit. So probably we want to move it into meters next. Anytime I am asked to change the unit, I want to draw myself an X and a line as the framework. So I draw an X and a line. Right now, I have units of kilometers to get rid of. So I'm going to put kilometers so that I have 1 on the top and 1 on the bottom here on the bottom. I also know that the unit that I'm trying to get to is to meters. I need to think in my brain about what I know about meters and kilometers. Well, if I have 1 kilometer, that means 1,000 meters. An easy little trick here is that the smaller unit goes with the bigger number. I know that a meter is a smaller unit than a kilometer, and I know that there's 1,000 in 1, so the 1,000 goes in front of the meter. So doing that math, that means that I now have 3 times 10 to the negative 7 meters. Still, that's a pretty small exponent, so that doesn't make a lot of sense to use either. So let's go one step further and look at mu m, remember micrometers. So I now have 3 times 10 to the negative 7 meters, and to change that unit, what do I need to draw? An X and a line as a framework. So I'm going to draw an X and a line. I have meters as a unit that I'm trying to get rid of. The unit that I'm going from is going to go on the bottom. So meter is going to go on the bottom. The unit that I want to go to goes on the top. So micrometers is going to go on the top. You would be given a chart that has this value here, or you could look back at the scale that I gave you, but remember that there are 1 million, or 10 to the 6th micrometers in 1 meter. Again, the smaller unit, here the micrometer, gets the bigger number. So that means that I have 3 times 10 to the negative 1 micrometers, which happens to equal 0.3 micrometers. Now that doesn't seem like very far, but remember that a femtosecond is 1/1,000,000th of a billionth of a second. So sometimes unitary rates aren't given to you, and instead you're given a unit factor. And your unit factor is essentially the same type of relationship, except that it doesn't have a 1 is one of the values. So a unit factor compares two quantities using a ratio, except the denominator is not a 1. 25 liters per 100 kilometers is your gas consumption, $1.50 per 12 donuts. Unit factors, just like unitary rates, can be used in calculations. I'm going to do a demo with you in class where I weigh out some magic peas. They're special science peas even, but I'm going to give you the data so that we can look at it now. So just like anything else that has an irregular shape that I can't put directly onto a scale, or it's not safe to put on a scale, I need to use some other vessel to hold them first. And like I suggested to you in the safety and measurement video, you cannot tear a measurement when you've got something heavy on it. Okay, you can't tear the scale when you have a significant mass like a beaker already on there. Instead, you have to take the difference between the mass of the beaker and the mass of the beaker containing the content you want. So I've got that there's 65.84 grams when I have peas and the beaker combined. The mass of the beaker on its own is 49.15 grams. So taking the difference between that, I know that the mass of the peas only, all on its own, are going to be 16.09 grams. Now what I didn't tell you already is that I'm looking at a situation where that's 50 peas. So I can set up one of two unitary rates. I can either use the unitary rate of 50 peas per 16.09 grams, or I can use the unitary rate of 16.09 grams per 50 peas. Notice I can change these unit factors into unit rates just by dividing them through. So now let's think about, well, which of these situations or which of these unit factors or unitary rates would I actually like to use? So now let's think about which one we're going to use if we start with 1,000 grams. So if I start with 1,000 grams, the unit I have to get rid of is the gram, which means that I want to use the value so that the gram unit gets canceled off. If I put the gram unit on the unitary rate on the bottom, notice grams on the top and grams on the bottom will cancel. That means that I'll be left with units of peas on its own. Okay, here's another question. Could you lift 1,000,000 peas off the ground? And really, if it's asking if you could lift it, it's asking about the mass as the end. And it's starting with 1,000,000 peas. So if I start with 1,000,000 peas, I need to use a unitary rate so that I can get rid of the p unit. So do I want the p unit on the top or on the bottom? Well, I want it on the bottom. I need to have the unit on the top and on the bottom in order to be able to cancel it off. So notice 1,000,000 peas at 0.3218 grams per pea is going to work out to 321,800 grams. In other words, 328.8 kilograms. That's more than any of the Olympic weightlifters were able to lift. So even the strongest of you, I'm imagining that's a no-go. So that actually is the basics of unitary rates and unit analysis. We're going to work through a lot of practice of this because it's a really important skill for the remainder of the year.